Okay. So the question is about normalization.
So present the screen, sir.
Those who have joined the Jamboard, you should be able to see it, right? Some of you are not able to join.
Oh, okay, sir. Writing in the Jamboard. Okay, okay. Sir.
Uh, Maybe some of those people who are. You see the Jamboard? What do you see? What did I share?
Blank page.
You see the Jamboard, right?
Yes,
Whiteboard.
sir. Yes.
So the normalization question that Swagatika has asked. So as we said that the state is basically some kind of a ket vector psi. Now this ket vector, or if you want to write down in coordinate representation, it will be some kind of a psi of x. Okay, so this is basically at this stage. It doesn't have to be normalized, but it has to be normalizable. But then we can normalize this. Suppose if you say that integral psi of x mod square dx in some region minus infinity to infinity, for example, is equal to some kind of a constant n, which is a finite constant, then we can write psi of x some tilde is equal to 1 over square root of n into psi of x. So this is basically normalized wave function. Okay. Now it is psi tilde of x modulus square integral minus infinity to infinity dx is equal to 1. Okay. Now probability has to be calculated only with psi tilde of x, not with psi of x. That is, you should not use unnormalized wave function for anything. You should always use only normalized wave function. So in quantum mechanics, this is what I said is a matter of discipline. Given a state, if somebody gives you a state psi of x, the first thing that you do is check if psi of x is normalized. If not, first normalize it. Only then use it for any other purpose. You want to calculate probabilities or expectation values, whatever it is, use it only after you normalize it. So this is very, very important. So there is no question whether what will happen to probability if we normalize the state, because you should not calculate probability with an unnormalized wave function. So you should always calculate probability with a normalized wave function.
Excuse me, sir. Sir, can I put some comment on it?
Yeah, yeah.
Sir, like, okay, I understood the fact that why we should normalize, as I had already discussed it with you in last class. So, but now I am thinking like whether all other postulates, like for a moment, like take that probability thing, that probability in a value need not to be one, like just consider. So, like, then what will happen to the expectation value? Like whether then if like I do not normalize, then why my expectation value should not be correct?
See, the point is, if you don't normalize, then it does not have a one-to-one correspondence with the probabilities. Because anytime when you want to talk about there is a link between probability and wave function, and this link is established only when you normalize it, because the total probability has to be equal to 1. If you don't normalize, then this correspondence breaks down, and hence your average values with this probability will not be the true average value. Now you may ask, okay, what happens? It will be some other number, it will be some finite number, but that is not same as what you have one-to-one correspondence with the probabilities. And it turns out that so if you do these calculations in theory and then do an experiment, and then when you try to verify, you have to have this correspondence established first and then do the calculations, so that you will have same results as you observe in the experiments come out from the theory.
Okay, so like then I just have another question. Like
Yeah.
when we normalize a particle wave function and then try to find expectation value, or when we find expectation value after normalizing, then isn't it like we are prefixing the value of expectation value, because we are limiting that expectation value, that okay, this after normalization my expectation value should be this only, because that's what mathematical constraint which we are putting initially itself when we are using a wave function, right?
No, it's not like that. See, let us come back to this question. Suppose I have an operator A, and let's say it has these eigenstates phi n and eigenvalues a n, and then let's say consider a general state psi, and then you have so then we said that your psi can be written as a linear combination of these eigenstates of A, and then we said that psi is normalized. That implies this so this psi and psi inner product should be equal to 1. Okay, and that implies I have some sum over m Cm star Cn by m by n has to be equal to. So this is basically psi. So psi is equal to this, but this is orthonormal, and hence this one is delta mn. It is basically sum over m and sum over n. So that is given by sum over m comma n Cm star Cn delta mn. So that means if you look at one of the summations, suppose sum over m, that in that summation only m equal to n term will survive. So that gives you that sum over n modulus Cn square is given by this. So this has to be equal to 1, means this has to be equal to 1. Okay, so this is the condition. Okay, now if this condition is satisfied, okay, if this condition is satisfied, then we can say that mod Cn square has probability that An comes out as result if capital A is measured. If the state is high. Now this particular statement, whatever I have put it in the box, this I can make only when this is valid. If this is not valid, then I will not be able to make this statement. Now once this statement we are able to make, okay, then your expectation value of A in psi is basically written like this. So postulates tell us that it is psi A psi. The denominator I don't have to write because this is normalized. Psi A psi, which is equal to, once again I have summation over m, Cm star phi m A phi n, and of course Cn. Correct. So that means that is equal to, what is A phi n? Phi n is an eigenstate of A. So that is equal to m comma n Cm star Cn An into delta Mn, because A phi n is An phi n. So this gives you sum over n mod Cn square into A. So this is the expectation value. So this is basically the same statistical interpretation that I have. Probability of An into An, sum over all possible n's will give you the expectation value. So there is nothing like prefixing here. If the state is normalized, then we have this situation. Suppose you have a situation where, suppose let's say psi is equal to some kind of a Cn phi n sum over n, but let us say that modulus of Cn square sum over n is not equal to 1. So that means it is what? That means this is not normalized. But then I would expect that is not equal to 1, but we should expect that this mod Cn square sum over n should be equal to some value n less than infinity. That means this must be a square summable sequence. Okay, so if that is so, then you define a Cn tilde as Cn divided by root n, such that sum over n Cn tilde mod square is equal to 1. Okay, if it is not normalized, that is, if psi is not normalized, now probability of An is not equal to mod Cn square. This is important thing to note. It's not equal to this. So what is the probability of getting An as the result is basically Cn tilde the whole square. Okay, so the interpretation of probability is linked to this normalization. If it is not normalized, this is not probability. And if it is not probability, then you should not use it in the expectation values. Correct? So this is what is to be kept in mind. You have to always use a normalized state.
Okay, sir.
Hello,
Now I
Chitti.
think I have a question
Hello,
like
hello,
how.
sir.
Yeah, one
Hello,
minute.
sir.
Yeah.
Sir, I have one small, like, I have to comment which you need to pass on, sir. You just tell if it is right or wrong. Sir,
Uh, yeah.
sir, what I'm telling is, we have defined the probability as one. Like, for example, he told that what happens if it is not normalized. This is
Mm,
my interpretation. I don't know if it is right or wrong. Suppose if the given wave function is giving, for example, we put it is equal to one. If it is not normalized, if it is the probability of mod c n square, let's say it adds up to some two, okay, or two or three, some finite number.
mm.
What I am telling is define the three or two as is its image as one. Like we can treat the three number as one because it is some finite number, and develop a similar sort of theory for probability, and we can say that it has some one-to-one correspondence, that one and three numbers, because it's just a finite number. I am telling that that whole interpretation can be done, isn't it, sir? My my way of I mean, I'm telling this. Is it possible or not, sir?
But
See, in
sir, may I
principle,
say something?
yeah.
Yeah, like at was Ritis told that if we are gonna take not one and another number, so I think that the whole concept is borrowed from probability. So if we are changing to another number, then we have to change the whole probability theory, not just number, right?
See, what I'm trying to say is that nobody will hang us if you don't normalize it to one. Okay, you normalize it to two, or you normalize it to three, or you normalize it to 10,000. It doesn't matter. Now the point is that there is a meaning for the probability equal to one. Total probability is equal to one, because when you say the probability is equal to 0.2, that means what? That means the chance. Suppose let's say probability I is equal to 0.2. That means chance for result to be AI is 20%. Correct? That is the meaning of saying probability is equal to 0.2. Now you so this is one thing. Suppose if I say that the result actually belongs to the set of eigenvalues, then you ask the probability that the result is going to be any one of these set of eigenvalues, then that has to be equal to 1. That means chance has to be 100%, because it cannot. Already we are saying that in quantum mechanics we cannot deterministically say anything. Now probability is equal to 1 is a statement saying that the result cannot go out of this set. That much is deterministic. Okay, so that much is deterministic. Okay, so that is something which uh, which is uh, uh, which is what meaning of 100%. The probability theory, why this one is important, because that is 100%. There is nothing beyond it that is possible. If you toss a coin, if you say head and tail, now you ask a question, what is the probability that you can get head or tail? Okay, then if you say that is equal to 1, that means it is 100%. That means that there is no other chance that is possible, or there is no other outcome that is possible. So in terms of the totality of the outcomes, we are certain. That is what it means. We are certain is guaranteed by saying the total probability is equal to 1. Now, what do you mean by if total probability is equal to 2? You have to go back and then redefine all your notions of probability. But this one is important because it is 100%. Okay, so that is what is the concept of normalizing it to 1. Now that is the reason why, in fact, whatever you are saying is a restatement of normalization. If the total probability is not equal to 1, if it is equal to 2, then you redefine your coefficients or redefine your wave function such a way that it is made to 1. Okay, so this is normalization as a concept is telling you that your wave function is normalizable is sufficient. You don't have to have a normalized wave function. A normalizable wave function is sufficient. You can always normalize it and use it. But since probability is an important ingredient of the theory, since total probability or total number of a set of outcomes is a certain thing, we should have total probability is equal to 1, and hence anything you do in theory with the wave function, you should always normalize it and then use the normalized wave function.
Yeah, okay, sir. No, sir. My question was that 100% can, like, 20% can also be written as 40 by 200. So similarly, why
That is
can't we?
normalization, no?
Yeah, that is normalization. Yes, correct, sir. But what I'm
Yeah.
telling is, in case if we define probability as 2, we can develop a probability theory equivalent to 1. That's what I'm telling, and we can redefine those. That is
That
what I was thinking.
no, that is precisely normalization.
Yeah, the concept remains the same, but I'm telling the finite number can be any number. Just because the mathematicians in those days defined it as 1, we take it to be 1. But we can do a similar sort of theory. That's what I'm telling. The number
No,
doesn't matter.
total probability is equal to 2. What does that mean? How do you interpret that? Do you want to say that there is a 200% chance? That may be sometimes okay in colloquial language, but mathematically it makes no sense, right?
Yes.
So that is the reason why it has to be 1. If you have any finite number, you divide it like 40 by 2. You said you divide it and then you make that as the coefficient half. Divide that by that number. That is precisely the normalization. So why people are asking you to normalize is for this reason, to make this wave function. Only when you normalize, your wave function is a probability amplitude. If you have unnormalized wave function, there is no relation between the wave function and probability. That means you are not doing quantum mechanics. I don't know what else you are doing with unnormalized wave function. You want to do quantum mechanics, you should normalize the wave function. And normalization by definition is that the total probability should be equal to 1.
And excuse me, sir.
Yeah.
So, like last class, we raised, like, you basically asked a question that whether the probability is quantum and like quantum number, like whether it's discrete or continuous. Like we had a kind of discussion on that.
Uh-huh.
So, like, can, like, looking now and understanding what is the importance of normalization on the wave function, can I, like, maybe colloquially or like more ignorant, can I make this statement that since all values of this wave functions are not possible in all regions, like where for some reason the wave function will be collapsed and some reason the wave function values will be there. So that makes me feel that okay, that probability should be more quantum in nature than this continuous in nature. Is it correct? This idea is correct, sir?
This idea is partially correct and partially incorrect because it depends on the observable. Okay? So suppose let's say that I have an observable A, and so I have this eigenstates of this observable an phi n. Okay. Now in coordinate basis, I could have written this as A, and this will be some phi n of x is equal to an phi n of x. This is an eigenfunction. Okay, that is a ket, and this is an eigenfunction. And what is we have seen yesterday or day before yesterday that this is basically projection of phi n along x direction, along x. So this is the definition of this function. Now you can ask a question that you have this So we had written some arbitrary state psi as sum over n Cn phi n. Okay, or equivalently, okay, so in terms of coordinate basis, I can write this as psi of x is equal to sum over n Cn phi n of x. Okay, this much is clear. Okay, now the question is, what is the probability that you are asking about? So psi of x is the state. Now you can ask, first question is, what is the probability of the property A being L? Suppose you ask this question. Now this is discrete. What is the answer? The answer is modulus of CL the square. This is the probability. Now A has discrete eigenvalues A1, A2, A3, etc. So the probability of this AL is a discrete probability distribution. Okay. In other words, if you try to write down, so let's say that you have probability distribution P of A, then you have A1, A2, etc., some AL, and so on. So there may be some probability for this here, there may be some probability here, there may be some probability here, there may be some probability here. Like this is discrete probability distribution. As you can see in the case of binomial distribution, for example. Okay, binomial is a discrete probability distribution. Okay. Now you can ask the second question. The second question is probability of finding the system at x. Okay, so the question is, what is the probability of finding the system at x in region dx? Suppose if you ask this question, then the answer is psi of x mod square into dx. Now suppose if you ask the question that, okay, suppose you have there is some a and there is some b, and you are now asking what is probability of x. Now this probability of x can be some kind of a function, continuous function like this, because psi of x is continuous function of x, and so is mod psi of x square. So if you ask a question about x, because x is having a continuous eigenvalues, so you can have a continuous distribution. Whereas the operator A that we have talked about earlier has discrete eigenvalues and it has a discrete probability distribution. So this is a continuous probability distribution. So this is the difference.
Okay, sir. I think I understood more it now. Thank you, sir.
Hello, sir.
Yeah.
Sir, one question coming to my mind, that can probability flow from one region to another region, sir?
Yeah. So, so let us look at that question. So the question is, can probability flow from one region to another? So let us look at Schrodinger equation. So let's say we have Schrodinger equation. Okay, so let me call this as in position position basis is equal to minus h bar square by 2m L square. Maybe I think I should simply use a one-dimensional thing. After that, we can generalize this. That is del square psi of x comma t by del x square plus v into psi of x. This is the Schrodinger equation. Okay, let's start with Schrodinger equation. Now note that psi is a complex valued function. Psi of xt is complex value. So I can actually take a complex conjugate of this wave function. Then I will get minus IH cross rho psi star of x comma t by dou t is equal to minus h bar square by 2m rho square by dou x square of psi star of xt plus v into psi star of xt. That means if psi satisfies this equation, psi star will satisfy this equation. Okay, so let us call this as equation 1 and this is equation 2. And now we can ask, so suppose you take 1 minus 2. So then what we will have is IH cross rho psi. Okay, before I do 1 minus 2, I multiply this 1 with psi star and multiply 2 with psi. Okay, then I have psi star dou psi by dou t plus psi dou psi star by dou t. So this is what we will have on the left hand side. This is equal to minus h bar square by 2m into psi star rho square psi by dou x square minus psi rho square psi star by dou x. And other term will anyway cancel because psi star v psi is same as psi v psi star. V is the real quantity. So this is what we will have. Okay. So now what we have here is left hand side. Suppose I take this IH cross on this side, then it becomes this I can write it as dou by dou t of psi star psi is equal to h bar by twice mi with a negative sign, bar by twice mi into, suppose if I write a dou by dou x outside, then I write psi star dou psi by dou x minus psi dou psi star by dou x. Okay, you see, if you do this, there will be dou psi star by dou x and dou psi by dou x. There will be one such term here also. Those two will cancel, so this will be same as this. Okay. So now what I have is, so this is about, suppose if I am going to define this as, okay, so I take it to this side. plus this minus becomes plus, this is equal to 0. So now if I define some Jx as psi star dou psi by dou x minus psi dou psi star by dou x into h bar divided by twice mi. And if I define that, then what happens is that this will be like dou jx by dou x. Okay, so now we can generalize this into 3 dimensions and then write this as an equation like this. Dou rho by dou t plus del dot j is equal to. This is, I think you are familiar with this in electricity and magnetism. This is called a continuity equation. Okay, this is called continuity equation, where this rho is equal to psi star psi, or this is equal to mod psi square. This is probability density function. Okay, and this j is a vector quantity which is given by h bar by twice mi into psi star del psi minus psi del psi star. Psi star del psi. This is called probability current density, probability current. Now, the way to understand this equation is like this. Suppose, let's say that there is some region in which your rho is defined. Now, this is some volume, okay? This is some volume, and this is the surface of that volume. Now, what does this mean? Dou rho by dou t is equal plus del dot j is equal to 0. This means what? Suppose I integrate this dou rho by dou t into d3r in that volume plus integral del dot j d3r in that volume is equal to 0. That means this is equal to dou by dou t of integral over v rho d3r. So what is this? This is basically probability in volume V. Plus, I can use Gauss divergence theorem and write this as a surface integral over j dot dA over the surface that is bounding this volume. That is equal to 0. So what this conservation tells you, that supposing that, so now I can write this as dou by dou t of the probability of this volume V is equal to minus integral over the surface S j dot t. Okay. Now what this means is that suppose P of V, the probability of in the volume V is changing. Okay, suppose if it is increasing. Okay, that means this is basically what? P, let me write this as PV at t plus some delta t minus PV at t divided by delta t. That is what this derivative means. Of course, in the limit delta t tending to 0 is equal to minus integral over the surface j dot dA. Now, suppose probability is increasing. Okay, probability is increasing. That means this is positive. Okay, so left hand side is positive. Okay, so left hand side, let's say, and then j dot dA. So if it is positive, that means j dot Ca has to be negative, because already there is a negative sign outside. Now j dot dA is negative means what? So j is into the volume V. So that means the probability actually comes from outside to inside. So it is like flowing from outside to inside. Now, if this is negative, that means if probability is decreasing, then j dot dA is positive. That means probability is going out from the volume V. Okay, so j is out of V. So this is how the probability actually changes from one region to the other region. The probability, it's not that it will disappear here and appear somewhere else, but this flow is continuous. At any point, if you find that the probability as a function of time is changing, that means it is going from that region to another region, exactly like how a fluid flows. So probability flow is almost like a fluid flow. Okay, so this is how we can understand how a probability actually flow from one region to other region.
Sir, is it same as
Sir.
a probability continuity equation?
Yes, yes. This is probability continuity.
Achha. And so this
Yes.
the idea that if probability is changing from one place to another, it means that probability is flowing. That this whole idea is that probability is flowing. Is it influenced with the normalization principle? Because net probability in volume should be one. So if with time at any particular location, if probability is increasing, means there should be that, as you talked of, plus delta j. So that should be come from some other reason.
Correct.
So is this like it to maintain the that idea of normalization overall?
Yeah, that is if you are considering the entire volume, so the total probability will be in the, that is P of this capital B, entire volume is 1, right? Probability in the total volume is 1. Now we are asking, suppose you take a point here and consider a small volume V, and now you ask a question how the probability of V is a function of time. It changes here. If it is decreasing here, it has to increase somewhere because the total probability has to be equal to 1.
Okay, that gives better picture.
Sir, in the previous page, the integral, like
Hmm.
generally how you are taking that derivative out, sir? Is there any particular reason how do you take the derivative out, sir? Yeah, in the first step, the dou by dou t, how you took it out of the integral. No, the next page, sir.
Here only, right? Dou by dou x I took out of the integral.
No, here I understood, sir. Next page, next page. Here I understood totally. Next page. Yeah, here's here. How did you take the dou by dou t out, sir, from that integral?
Yeah.
Like,
So the derivative
any
is with
particular
respect to time, and
and
integration
integral
with
is
respect to
respect to
space.
r.
Yeah,
Uh,
they are independent.
Independent. The other part I understood is this Gauss divergence theorem. So that's
Yeah,
understood.
yeah.
So here basically we are trying to interpret this flow of something in terms of probability. The probability is flowing from one point to other.
Yes.
So that's how we were interpreting.
Yeah.
Sir, I understood, sir. Sir, it's enlightening, sir. Another question is coming in my mind. Sir.
Hmm.
Suppose we have considered this system, a box,
Hmm.
and there is a wave function.
Hmm.
And if we operate a position operator
Hmm.
as the probability, which is 100%, it will somehow flow and clump together in a position to give the position after measurement.
Um, I'm not sure if I understood what you're asking, but let me see. So I'll try to interpret your question and see if if I understood it correctly.
Sir, can
Suppose
I say,
no,
say again, sir?
no, I will tell you if I have not understood correctly, then you tell.
Okay,
So
sir.
let us say that this is the region, and then you have some wave function in this region, psi of x. Okay. Now we can talk about of probability of the particle, probability of let us say location at x in region dx. Dx is given by mod psi of x. So we are always assuming it is normalized. So let's not go back to normalization business again. This is a normalized state, and so this is the probability. Okay, so um, this may be different, and when you actually plot this probability density from 0 to L, it may have some kind of a probability function like this. It may be something like this. Okay. Now, if you ask what is the probability that the wave function, the particle is located here, so this is your mod psi of x square. Okay, so if you ask in this region, it is this value. You ask in this region, it is this value. You ask in this region, it is this value. Okay. Now you are bringing in the concept of measurement. Suppose you measure x, then you find that is you find the result. You find the result to be, let's say, x naught. Okay, so that is a particular value here. So let us say this is x naught. You find that result. Okay, then the wave function after measurement. Wave function after measurement is given by, or the wave probability distribution after measurement, or psi of x naught square is going to be x naught okay. So now the question that you are asking is that, well, let us call this as figure 1, and let's call this as figure 2. I think your question is how figure 1 goes to figure 2 when position is that your question?
Yes, sir. Meaning is same.
Huh?
Sir, meaning is same. Is the 100% probability somehow clumped together in a position?
Yeah. So that's what your probability, which was a distribution like this, as is shown in figure 1, is
Yes.
now somehow is 100% at x naught. Okay.
Yes, sir.
How does it change? How probability clusters? in this kind of a case, right? So I wanted to understand your question. That is why I spent this much time, but only to tell you that I don't know the answer, because we really have no idea of how this clusters. So what quantum mechanics tells you in terms of that, what is called collapse postulate, that is postulate number 5 in our discussion, is going to tell you that you had some wave function psi of x before measurement, and now after measurement you have a different wave function. So after measurement of x, then your wave function is delta of x minus x. So you say that the wave function collapsed from psi of x to delta of x minus x. Okay, and nothing more we know about it. We do not know what is the mechanism, whether the probability is collapsing or the wave function is clustering. All these things are like it is like we are going to describe some non-existent mechanism if we describe anything. Okay. So it's one of those tough questions. We don't know the answer. It is nevertheless good to ask, but there seems to be no well-defined answer.
Yes, sir. We have to explore more on it.
Correct.
Excuse me, sir.
Yeah.
Sir, is it possible to find the probability of finding a particle within the two states?
Within the
Two states.
what are the two states?
Sir, for example, if an electron is there in a particular state, and for a fractions of second, and we are applying a current, and the electron is taken from this state to another state, and if you want to find the probability of the part of the electron in the initial state, then is it possible?
Okay, I think your question is essentially related to can a particle exist simultaneously in more than one location. Is that correct?
Yes, sir. And I also asked whether it is possible to find the probability in any state, in any one of the states.
So can we find probability? Okay. So I think the present understanding is that answer is yes for both. Okay, so you can have a particle existing simultaneously in more than one location, and you can also find their probabilities. Because see, when we are trying to say that this modulus of psi of x square x has some kind of a form like this, that means what? This is the probability for finding it here, this is the probability for finding it here, this is the probability for finding it there, this is the probability for finding it there. So now one can ask the question, what does that mean? Does it mean classically, if we see a probability thing like this, classically, what do we say? Classically, we say that we do not know. This is basically ignorance. Okay, we do not know where the particle is. we only know probabilities of possible locations. This is basically what we do in classical statistical mechanics, or classically whenever we use probability. In quantum mechanics, particle can be there in all locations simultaneously and we can determine probabilities of the locations which can be found when measured. So this is how we do this in quantum mechanics. Okay. Now, it is a little subtle point that why we should assume that they should be there in all locations, because so this way of saying is there are experimental results that back such interpretation. Okay, so one of the experimental results is what we discussed earlier. That is, you remember that we talked about having a source here, and then you have a beam splitter here, and let's say you are getting a photon, and then these photons are coming like this. Then you have a mirror, and then there is another mirror, and you have another beam splitter. So let's call this as beam splitter 1, and then this is beam splitter 2. This is mirror 1 and mirror 2. Now this is transmitted, this is reflected, and you have transmitted, reflected, plus reflected, transmitted beams will come. Let's call this as D1. And then you have transmitted, plus reflected beams will come here. This we call it as D2. Now the observation is that D1 will get all photons. It's 100% of the photons come here, and D2 gets no photons. Now, if you want to understand this result, you must say that the photon has traveled. So let's say this is path 1 and this is path 2. So photon has traveled both paths simultaneously. If you try to measure which path it has gone, then you will get which path information, but you don't get this result. You get 50% here. So this is very sensitive. Okay, this is basically interference. Interference is one detector showing you maximum, other detector showing minimum, and this particular experimental setup is what is called as Mach-Zehnder interferometer. Okay, so this can be mathematically, this result can be mathematically derived, which we will do in some other when we actually look at this problem. But this is something, this kind of an experimental indications are there that which says that the particle can be there in all locations simultaneously, and we can determine the probabilities of these locations, which can be found. The locations can be found when we measure them.
Hello,
Excuse
sir.
me, sir.
Yeah.
So like I just got more confused when Genu asked like whether one electron can exist into two energy states. So I think that how that is possible, because when in order to find the energy level or energy, we need to apply a energy operator on the wave function, and when we apply operator according to postulate wave, it must have to reduce to one state. Like the wave function must collapse. So
That
how
is
we
that is only if you measure, no? If you don't measure it,
but how do we know that they to exist without measuring?
yeah. So if you do, so how do we know if it exists in that superposed state? So that means if you make measurements different times on systems with the same state, you will get different results. So if your energy shows dispersion, that means it is in a superposition of energy eigenstates.
But then, sir, how the word simultaneously will be justified if we are like taking the dispersion into account?
See, what is the energy of the system? So like that, if you ask, okay, this word simultaneously is a little bit. I would have preferred not to use this word. Okay, simultaneous has got some problem because it is related to time. Okay, so let's not worry about simultaneous. You say that there are more possible values of position, or more possible values of energy for that matter. So don't confuse simultaneous with time. Okay, so let's not worry about that word. So let's say
Yeah,
can particle exist in
now,
more than one location?
yeah, now it's clear, because I was thinking on that is like how simultaneously we can measure two measurement of one particle.
Yeah. That's correct.
Okay, so thank you.
Sir, I have some basic questions.
Huh.
So, why do we prefer momentum position all the time we're taking consideration? Like, why not other physical quantities? Like, as per coming to uncertainty principle, we have taken some position, momentum, and then energy, time. So, is there any specific thing that we follow that we have to take position with relate to momentum and energy with to time, like that, sir?
Yeah. So we are actually guided by our classical understanding, right? So classical mechanics tells us that you have some kind of Q and P are canonical, the state of a classical system, right? State of a classical system. Okay, so we make a jump from classical system to quantum system, but we would like to treat those cases which we know classically, right? So that is classical correspondence is very important. So in quantum mechanics also we have similar variables Q and P. Okay, so we were calling X and P, I think. So we call it as X and P. So now we say that we have X and P, and in classical mechanics, you know that X and P are canonical coordinates, and E and P are also canonical coordinates. This time evolution is like a canonical transformation. This you might have seen in your classical mechanics course. So time evolution itself is like a canonical transformation, where the canonical transformation is affected by nothing other than the Hamiltonian. So Hamiltonian is the total energy of the system. So E and T are canonically conjugated. Now the structure in classical mechanics is something like this. So you have QP is the state, or XP is the state, and then a property of the system is always written by a function of x comma p. Okay. So this is x comma p is a function of x comma p. So one generally calls this as a dynamical function. Dynamical function. Okay. So one of the important property that one of the important property is the Hamiltonian itself. Hamiltonian is a function of x comma p. Now you can talk about set of all functions. Okay, so I'm going to define some D as set of all functions f of x comma p, such that this f is I will call it as a gamma, which is a phase space to real numbers. So gamma is a phase space. That means for every point in phase space, there will be a real number. So this is your D. Now you can ask a question like this. Suppose given f, this property at time t equal to 0, how to find f at time t? You can ask that question. Now I can do this in one way. For example, I ask what is df by dt. I can write it as dou f by dou x into x dot plus dou f by dou p dot. But you know, in Hamilton's equations, your x dot is equal to dou h by dou p, and p dot is equal to minus dou h by dou a. So if I substitute that here, then I will have f dot is equal to dou f by dou x into dou h by dou p minus dou f by dou p into dou h by dou a. And this is what is called a Poisson graph, f with h. So this has got the name called Poisson graph. I'm sure you have done this last semester, but just I'm trying to. So that means f dot is equal to f with h. Now I can write it in the following fashion: f dot is equal to some operator h acting on f. What is the action of this operator? Action of this operator is taking the Poisson bracket of this with h. Now, just like Schrodinger equation, I can solve this formally. Okay, so I can write down df by f is equal to h operator dt and integrate this. This implies my f of t will be equal to e to the power t h acting on f of 0. Okay, so this is how I get f of t. What is this h operator? This h operator is basically the Poisson bracket operator. So I can say that my f of t can be written as 1 identity plus t h plus p square by factorial 2 h square and so on, acting on this function at 0. Okay, so that means what? Okay, so that means what? That means we have f of t is equal to first f of 0 plus t times h acting on f plus t square by factorial 2 times h square acting on f, and so on. So that is equal to f of 0 plus t times the Poisson bracket of f with h, that is the action of h acting on f, plus t square by factorial 2 times Poisson bracket of f h okay, f h and its Poisson bracket with h, and so on. So if you just by calculating the Poisson bracket of with h and its Poisson bracket with h, etc., 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 you will be able to find out from f0 ft. Okay. So now this Poisson bracket operation, that is for some f of x comma p and g of x comma p in this set of all functions d, you can define this Poisson bracket fg, okay, and that will be also in d. So this is a new binary operation in this d, okay, but this new binary operation is closed, but it is not associative, because you can show that with this Poisson bracket you have a relation like this: f g h plus h f g plus g h f. Okay, so this is equal to 0. That means the associativity is not there. So this identity, as you might have proved it in classical mechanics course, this is called Jacobi identity. So this Poisson bracket will satisfy something called Jacobi identity. Okay, now the vector space of functions which satisfy this kind of we have a binary operation, a bracket like Poisson bracket can be defined which satisfies this Jacobi identity. Then we say that this structure D, is actually called a Lie algebra. Okay. Lie algebra is another algebraic structure, so it is called a Lie algebra. And to define a Lie algebra, you must have a bracket like this or an operation like this which satisfies Jacobi identity. So this D is a Lie algebra. Now, why I am saying all this is that in quantum mechanics, when you go to quantum mechanics, every function x of p, there will be some Hermitian operator. Okay. Now you will have set of all Hermitian operators, okay, and more, because now let me call this as dq, which is set of all Hermitian operators corresponding to this classical phase space functions, okay, corresponding to all dynamical functions. This is one, and then there is also another one. Okay, other operators that do not have classical analog, like spin. So we cannot find any f of x comma p for spin, for example. This is a quantum mechanical property and which does not have any classical analog. So you have dq, which is a much bigger set. Then here you can talk about a commutator between two operators, a comma b. Okay, so this is the bracket that we will use here, and this dq also becomes a Lie algebra. So whatever is the role played by Poisson bracket in classical mechanics is played by a commutator in fact, this is how Dirac introduced what is called canonical quantization. So he said, you take a Poisson bracket between any two elements and replace it by commutator divided by IH cross in quantum mechanics. This is what is called canonical quantization. Canonical quantization. So you have a classical system, you want to quantize that system. This is one way of quantizing the system. Replace all your Poisson brackets by commutators. Okay. So this is how you have classical correspondence. Wherever there is a classical correspondence, there we have this xp have to be honored, and we have to find the corresponding operators in quantum mechanics. Now, this structure is something at this level. You have both quantum mechanical properties and classical properties, all of them at a very abstract level, they are just Lie algebra.
Thank you, sir. Sir, I have another doubt.
Yeah.
That before starting the quantum mechanics, some people says that it is the study that we study at microscopic level. So, is there any limit? I mean, and dimension we are having that we can say that up to this dimension we have to study in classical mechanics, and up to this dimension we have to study in quantum mechanics. Is there anything like that?
Yeah. So now to understand that, we have to look at this. The quantum mechanics is relevant. So there is something called this Planck's constant, right? So this Planck constant is called quantum of action. Okay. In other words, one of the very important the result of quantum mechanics is that quantum mechanics tells you that there is a lower limit. There is a lower limit on action. Just like special theory of relativity tells you, there is an upper limit on the speed, right? So there is an upper limit on the achievable speed. In the same way, there is a lower limit on achievable action. So this is important to understand. Now suppose, let's say we have a system. Okay. Now from the physical variables of the system, okay, from properties of system, construct a system action. I am calling this a system action. Okay. So I'm going to tell you a recipe. Okay, construct a system action and compare system action to H. H is the quantum of action. Okay. Now the recipe is, if system action is comparable to that of H numerical value, then quantum mechanics is necessary to address such system. Now, if your system action is much greater than this H, then classical mechanics is adequate. Now, let me illustrate what this system action is in some example. Suppose, let us consider a laboratory pendulum, whatever experiment that you have, laboratory simple pendulum. Do we do quantum mechanics for this? We don't do it. Okay, so let's ask a question, why? Now, in a laboratory pendulum, let's say that we have some kind of a pendulum, which is, let's take the mass of this pendulum to be, let's say, some 1 kg. 1 kg is too big, I think. So let's say 100 grams or 0.1. Okay, so this is the mass of the pendulum. Now, we know many properties of this pendulum. No, the pendulum has got certain energy, it has got time period, and so on. Now, typical laboratory pendulums, let's say our time period is of the order of 2 seconds. 2 seconds is the time period. And what is the energy? Energy is equal to half k square, where basically this is half mg. So what is the potential energy of the pendulum? So that is mgl into 1 minus cos theta. This is the potential energy, and when theta is some particular value, theta naught. Okay, let us say theta is equal to pi by 2. So you lift it to that height. So then this becomes 0. So this simply will be mg into L. So that is equal to, let's say, 0.1 grams, and this you call it as some 10. And then length you can keep it as some 50 centimeters, or you can say 0.5 meters. So this is basically equal to 0.5 joules. Okay, so this is your potential energy. Now you can see that dimensionally, dimension of action is actually equal to dimension of angular momentum. Correct? So I can use this E and T, multiply them. This is joules and this is second. So joule second is basically angular momentum. So I define my system action to be is equal to E times T. That is equal to 0.5 joules into 2 seconds. That is equal to 1 joule second. Now remember, 1 joule second action is a very big action compared to h. So you see h is of the order of 6 into 10 to the power minus 34 joules second. So when you have, this is 10 to the 34 times bigger. So that means what? It is coming in this calculation that h is much, much greater than this h. In other words, you can say that the h by system action tends to 0. So there is no quantum mechanics required for understanding a pendulum problem. Okay. Now let us look at let's look at black body radiation. Okay, so let's look at black body radiation. Now, black body radiation, we had something like lambda max into T is equal to a constant. This is called Wien's constant, right? This is an experimental result. And what is this constant? This constant is something like 2.8 into 10 to the minus 3 some units. Okay, that is meter Kelvin. Some units like this. Now, you want to make this into energy into time, right? That is how you want to. This is already lambda max is c divided by nu, right? So suppose if I multiply this one with the Boltzmann constant kb and then velocity of light c, then kbt is energy and lambda max by c is basically time. So that means this numerical constant I will multiply with kb. This is a constant, right? This is c. So that means this is equal to 2.8 into 10 to the minus 3 into kb is some 1.3 into 10 to the minus 23. Right? So that is Boltzmann constant divided by 3 into 10 to the minus 10 to the 8 meters per second. So this is 26, and this, if you see, is roughly 10 to the minus 34. So you see that here, this is your system action. Okay, so this is your system action. So when I look at the system action with an experimentally determined Wien's constant, system action is of the order of the quantum of action, or the Planck's constant. So quantum mechanics is needed. So this is how we determine if the quantum mechanical effects are important or not important, by constructing something called a system action and then comparing the system action with the quantum of action. So if you use that, then you will be able to decide whether quantum mechanics has to be used or it is not required.
Thank you, sir. You have nicely explained this one.
Yeah.
Sir,
Yes.
I need an explanation or clarity. At what point in studying quantum mechanics the idea of abstract algebra or abstraction is needed?
Basically, abstraction is needed at every aspect, but only thing is that, for example, all that we have discussed in terms of these postulates, etc. Suppose if, let's say that we don't understand all that. Now, where do we find a problem? We will find a problem in trying to interpret the results. If you don't understand this, then interpreting the results will be. Otherwise, if you simply know, okay, I know how to solve Schrodinger equation, I know how to take expectation values, then you can still do quantum mechanics. You can still do reasonably well quantum mechanics. But then if you understand all the postulates and then basic structure of quantum mechanics, then interpretation of that will become easy. Abstraction is always a useful thing to get used to.
Okay, sir.
Sir,
Yeah.
sir, I have a doubt. Last class you said that in a stationary state, the expectation value is a constant in time. So does that mean that if I take the position operator and I measure for a particular particle at a time t, I'll get a set of values and I can calculate the expectation value from that. And after a time interval of delta t, and I again measure the position of that particle, then should I get the same set of values so that the expectation values are same?
No, may not get same set of values, but the average of those values will be same.
But after one measurement, shouldn't the system alters? I mean, observation alters the system. We say like that. So
No, see, one thing is that what I'm trying to say is that your let me put it this way. Suppose, let's say that you have a system and you are measuring your position values. Okay, let us for an argument's sake, let's say that you measure you get your position values -1 and +1. Okay, so what is the average value of x? Average value of x is 0. Assuming that this has an equal probability, average value of x is 0. Now suppose this is at time t equal to 0. At some time t is equal to some delta t, you may say that your x becomes now -1.2 and this becomes +1.2. The values are changing, but then the average value of x is still 0. So this will remain 0 for a stationary state, but this need not be same. That means it will vary in a symmetric fashion. So that is what it means. Expectation value can still be independent of time, but the position values need not be independent of time. And this is not related to collapse, because when we say that we are getting different values, that means we are not measuring on the same system. So that is why I always wanted you to understand that we are getting, let's say, a stream of particles. Okay, a stream of particles, and then you make a measurement. You measure x. Now all these stream of particles are in same state, psi of x, psi of x, psi of x, like that. Okay, and each one of them you measure, then you get different values. Take average of those values. That is how you have to understand. If you are measuring on this particle position, then the position is collapsed. After that you measure, you will get the same position. So we are not measuring on the same particle. We are measuring on a collection of particles which are prepared in the same state.
okay, sir. So, sir, if the expectation value of position is constant, can we say that the expectation value of momentum is 0 in that system?
No, we cannot say like that, because why do you come to that conclusion?
Sir, because I thought that the time derivative of position is velocity and momentum is related to velocity. If expectation value is a constant, then it's constant in time, then its time derivative should be 0. So the momentum expectation value should also be 0. I thought like that.
Okay. Possibly, I don't know if we can write a proof like that, but let us say that for some state psi of t and x, psi of t, is same as psi of 0 Okay. Is what you want to say. Then if you ask maybe it is possible to show that let me see. The question that you are asking is that if this is so, can we show that psi of t e f t 0? It looks like there is some meaning in the question, but I'm not able to write. I'm not able to think of the proof now. Okay, so anyway, let me think about it. I will try to see if I can come up with an answer either in favor of this or saying that it is not so. But I'm sorry, I don't know the answer.
Okay, sir.
Sir,
Yeah.
sir, in your when you wrote that H Poisson bracket, sir, that one.
I don't think I have erased all that I have written because
No. Last page, sir. You go to the last page. You have written the Jacobian entity. That one. I mean, the first page. In the first page. You again start with the first page.
because this Jamboard will allow you to write only 20 pages.
Yes. The first page of the blackboard, sir. First page.
Yes.
So there, how you wrote that instead of H square, you wrote FH comma H, sir. That one I was a little bit confused. The first step I understood. The second step I'm not able to understand how you wrote the Poisson bracket FH comma H.
Okay, so that is it is like this. H square acting on F is like H acting on H acting on F, right? H acting on F is basically Poisson bracket of F with H. So H acting on this one is basically Poisson bracket of F H Poisson bracket with H. I am just using this definition of HF equal to F with H, Poisson bracket of F with H. Now this is like a new function now. That new function is Poisson bracket with H.
Okay. Okay. Okay, sir. Okay, sir. Now this is something related to the interpretation of quantum mechanics, sir. So when we are doing the measurement process, we all were a little bit. You yourself told that the many like confusions are going around in the formulation itself. When we try to interpret that.
I could not hear you. Can you? There is a disturbance in the audio.
Can you hear me now, sir?
Yes.
Hello.
Yeah.
What I'm telling is we ourselves had a confusion about that particles existing simultaneously like that when we do measurements. So, but I read about something called as many worlds interpretation, where they came up with idea that all quantum measurements are existing, but what happens is each measurement will correspond to one new world or new universe. Like that, I think Sean Carroll, I think not Sean Carroll, Everett. I think it's Everett. Yeah, it's Everett in 1956. So he has formulated this many world theory. So I when I read about something in that, I think that this many world interpretation seems to be a very good explanation of this whatever confusions we have in regards to this collapse of wave function. Don't you think that interpretation seems to give some sense, sir? Like, I want to know about your ideas. Whatever I read, I felt a little bit convincing about the idea, because experimentally don't know how we're going to prove it, because multiverse existing means we have to, I don't know how it is possible, but that idea seems to make some sense, sir. Like, what is your take on that, sir? I mean, if there is a loophole, what do you think will be the loophole in that theory, sir? Because when I read, I found it convincing, but many people are against it. Can you give me one point where it says that that theory has some loopholes?
See, the important aspect is that the many worlds interpretation or many worlds theory of quantum mechanics is not just the interpretation that different particles or different experimental outcomes are understood as different things happening in different universes. Actually, that has something more in the sense, uh, for example, if your system and the experimental apparatus and the scientist who is observing and the laboratory in which it is observed and the universe in which that laboratory is there, all is in one universe. Now one has to make a replica of this entire setup in another universe. So the theory assumes that the observed observer laboratory universe is all in different replicas. So one of the problems of the theory is that if for example, if you look at Einstein's E equal to mc square, if so many copies have to be there, where is that much energy? There is no way to understand if that energy is there. Is there any way to know that such an energy exists? So in terms of energetics, I think that is one of the difficulties of the theory. Okay, so that is, of course, experimentally it is not. It's only an interpretation at this moment, but that is one aspect. Other aspect is that if you say that your experimental results that are, let's say, as I told you, that you have a stream of particles. In the first particle, let us say you are getting A1. That means in your universe you are observing A1, and in the second particle you are getting, let's say, A2. That means in the same universe, within the first particle and second particle, how things have changed, the environment has changed such that the change in this is happening, and this change within that short time has to take place in all the universes. So these are some issues which are little unsettled in my understanding.
Yes, sir. Because when I read about that, I felt a little bit convincing, because I mean, I want to know about some loophole of these theories. So I just
Especially many people who are presently working in this quantum computation, they seem to tend to give this kind of a many worlds interpretation. Especially David Deutsch, who was kind of a pioneer in this quantum computation area. He is one of the very strong proponent of this many worlds idea. Okay, but this is one of the candidates, but there are other candidates.
Sir, I feel that if that happens, then if every measurement will split the universe in different parts, so every action happening in this universe will split in different parts of realities. So how can it happen?
So that part is, how can it happen, is something which we do not know. But if so, whether it is splitting the universes or universes are already there, and then it is happening in those different universes. But anyway, I do not want to introduce more confusion into the course. And I think if you go to philosophy department, there are some courses on philosophy of quantum mechanics. I think they will definitely talk about these issues. What is reality? What is ontology? What is epistemology? And what elements of quantum mechanics are supporting reality and what is not supporting reality? But I think I will not address these questions or these issues in my course, because my course is supposed to teach you skills that you can use as per the existing knowledge, as per the practicing. So I would like to inculcate some skills which you can use. Basically, you should be finally able to calculate expectation values and probability amplitude. And that is what I think is the aim of this course. Other questions are important, and I recommend you think about it, read about it, but we will not have an occasion to consider them in our course.
Hello, sir.
So actually, as we were reading about measurement process, this came into my. I mean, there are some mathematical proofs too given by Everett. So I felt that
Yeah,
this
but
might be.
I would say that it is beyond the scope of this course.
Yes.
Gokulakan?
Hello, sir.
Hi.
Sir, I have two doubts. First is the L square AB and the L square R. The spaces are the two spaces are the same or different, sir?
They are different in the sense that when you take so when you take L square of AB, this is set of all functions f of x such that f is from a closed interval AB to a complex number. Okay, and L square R is same thing, that f of x such that this function is from set of real numbers to set of complex. So in that sense, these functions are different because the domain of the function here is interval AB, and the domain of the function here is the entire real line.
Oh. So the L square AB is having a limit.
The domain is AB.
Okay.
That is, your function is defined from interval AB to C.
Okay. Here the scalars are complex numbers, sir.
Correct.
Hello, sir.
Here it is.
Yeah.
It is mapped to what, sir?
Yeah, AB to C, complex numbers.
Complex number to complex number.
Which one?
The L square AB, sir.
Yeah, AB to complex means in your real line you have AB. So this is an interval. For every point in this interval, you will associate a complex number.
The AB interval is what, sir? Real number or real line? Okay.
Real line. Yes, AB is just a real line. So AB is a subset of real line.
Okay. And my second question is
The
why square integrity is necessary for normalization? Why is not square summability?
No.
Square summability.
Both square integrability and square summability are required. Just like we talked today in response to one of the questions. Suppose if I have, so let us say I have a state psi, which is written as sum over n Cn into phi n. Okay. Now the Cn is like a sequence of complex numbers. Now this sequence, psi has to be normalized. That means this psi has to be normalized. It implies my sum over n Cn mod square. There are infinitely many. This has to be less than infinity. That means this must be square summable. It has to be square summable. Right? So if it is square summable, only then this psi can be normalized. So I think this is less than infinity implies this. So if I want psi to be equal to 1, this implies my psi Cn mod square should be equal to 1. This is possible only if it is square summable. Now, on the other hand, if you say that I have a psi of x, that is a coordinate basis wave function, psi of x. Then I have psi of x, sorry, I have mod psi of x the square and integral. Okay, so let's say a to b, if it is L square AB dx, this should be less than infinity for this to be normalized. So this is basically square integrable. This should be square integrable. Now, if this is there, only then it can be normalized. If it is infinity, then you cannot normalize. Correct? So square integrability and square summability are necessary for normalization.
Yes, sir. And the wave function may be a square integrable function or a square summable function, sir.
Yeah. So when you say wave function, we always talk about a coordinate basis wave function or a momentum basis wave function, right? So that is always square integrable. Essentially, it is like this: the basis in which you are trying to expand your state, if it is a continuous basis like position and momentum, then it is square integrable. It has a discrete basis like any other quantized properties, then it should be square summable.
Okay, so it can be both. Sorry, it can be any one.
Yeah.
Thank you.
Hello, sir.
Yeah.
Sir, in this double slit experiment with a single electron, if we put two detector on two slits, then if the wave is impacted on one detector, then the other part, the wave function is spread over these both detectors, and if the wave function is interacted with the one detector, the other part of the wave function, is it come to the first detector, or it will say it's like we are not interacting and move away, something like that.
Yeah. So I'm not sure if I have understood your question, but I think you are asking something like this. You have a two slits arrangement, and you have a detector D1 here and detector D2 here. And then you have a screen. Now let's say that you have only detector D1, right? So if
Yes,
you
sir.
have a detector D1, now you are asking whether the wave function, so let us say this is psi 1 of x and this is psi 2 of x. So now you are asking is psi 2 of x present at D1? Is that the question?
Sir, it's like in other way we say that if a function psi equal to a1 plus a2 plus a3 plus a4 and like that state, the a detector is there, then if we detect, if the detector is detecting the state a1, then is that all the other states are converted to the first state, or the other states are leaving like that, or it contain only the single state?
Yeah, so I think you're asking exactly same question which Arup Jyoti has asked some time back, that what is happening when you do a measurement, whether they are escaping or, so that is essentially when you have this psi is equal to m over n cn phi n. Okay, when you have this thing, then you measure A, and then get some AL, then post-measurement state is phi L. Okay, so now your question is, what happens to other things? Are they running away, or are they getting converted into this?
Yes, sir.
Okay. So I think you ask this question in any changed language, I don't have answer.
Sir, okay, then the side 2 side there is a D2, and we have only one electron. Then the electron must interact with only one dictator.
Yeah. So the point is that see, let me tell you what we know. Suppose if you have detector D1 here, okay, and then
Yes.
you have no interference here. You detect the particle coming out of slit 1, then you don't have interference. If you don't detect the path, then you have interference. That is what we have. I mean, that is what is experimentally observed, and that is what quantum mechanics gives you also. Okay, but anything more than that is something which uh, we don't have a way to find out.
Yes. So, sir, then is there energy is associated with this wave function? Then if it is collapsed to a one point, then energy is I think it is the energy is evenly distributed with this wave function. Then according to energy conservation, we must say that there is a particle is in a one point.
Okay, so you're asking, is energy conserved? Is energy conserved in measurement process?
Yes, sir. I'm thinking that if we measure energy at one point, then rest part of the wave function's energy is leave like that.
Yeah. So the point is that it is not that it has a fixed value of energy, because if it is an energy eigenstate, then we can say, okay, it has a fixed value of energy. But otherwise, it may not have. It may be dispersed in energy also. Okay, and when you measure it, that dispersion. But also in a measurement process, we are interacting with some other system called apparatus. So the conservation also has to be considered only as a total conservation of both system and the apparatus. So sometimes if you look at the system alone, you may not see energy conservation for that system, because two systems are involved here. Same thing is of course also true with respect to information. Is information conserved? That is also not conserved in the system. Information also is exchanged between the apparatus and the system.
Sir, again, what about how we imagine the Hilbert space? Sir? What is the basis or dimension of this Hilbert space? If we apply some operator, we get some momentum and energy. But
so the point is that I have been doing this mathematics for the last 3-4 lectures. Stick to mathematics. There is no need to imagine. You just should know the rules of the game. That's all. Play it. If there is any imagination, the imagination will be different for different people. You may imagine it in one way, I may imagine it in a different way, and my imagination may not be convenient imagination for you. So that is something a very subjective thing, right? What is not subjective is the set of rules.
okay, sir. Sir, last question is, in older days, my mom asked me what is quantum mechanics. I tell her some like this energy is condensed equal h nu and something like that. After this Hilbert space, I don't know how to explain what is this quantum mechanics.
So that is a challenging thing for you, no? So you should
Yes, sir.
tell your mother what Hilbert space is. That is the assignment for you.
Already I teach him the group, but anything else is nothing happen more.
Okay, but anyway, in the lockdown, don't get kicked out of the home, but try. See, the Hilbert space is important for us to understand quantum mechanics, but that's not the only way to understand. See, if you look at some popular books, people keep saying that quantum mechanics is this, that, in different languages, different things, right? So also try using your communication skills to avoid Hilbert space and still talk about quantum mechanics. But as a physics student, of course, you should definitely learn what a Hilbert space is, because all quantum states form a Hilbert space.
Thank you, sir.
So any other question?
Sir, I have two. I think I have two doubts, sir. One thing which I forgot to ask last time. Last time when you talked about the Planck scale, remember those 10 power minus 33. If it is very much higher, we told that it is equivalent to classical mechanics. What happens if it is much lesser than that, sir? Like much lesser than. We didn't talk about that.
Of that order or anything less than that is quantum mechanics.
So anything less than 10 power minus 34, we can use it for quantum mechanics.
If it is very less, then you have to use. If it is very less, then you have to use something called relativistic quantum mechanics. If it is even less, then you have to use quantum field theory.
Sir, that h cross upon 2, is it experimentally proved, or we are deriving with the postulate of quantum mechanics? As in the third postulate of quantum mechanics we are having, we define delta x there, and we are using the postulates of quantum mechanics, then we will be using it to find delta x, then delta px, and then will be we define that whether it is greater than or equal to h cross upon 2. So my question is that is it derivable that we are taking in consideration, or it is experimentally showed that the thing is happening in this h cross upon 2?
I think the originally the answer was obtained based on some experimental proofs. Okay, I think the uncertainty, when Heisenberg thought about it, I think he got that estimate by looking at what are called atomic spectra, and then there is something called ridge combination principle. So the Heisenberg's work in getting this h cross by 2 was kind of empirical in nature. In the sense, he looked at experimental results, and then from there he said that this is how it has to be. But now we can derive it. Now we can derive it many ways. So now it is possible to derive, but originally I think it was, the idea was abstracted from the experimental results.
Okay.
Sir, and I think there was one question. If the stationary state expectation is 0, what about the expectation value of momentum? Is it equal to 0? Some stationary state is equal to something. There's a question mark, sir.
Yeah.
I think the answer to that is I have solved for harmonic oscillator particle in a box. In all that case, it's equal to 0 only. But there is an extra exception. When it is particle in a ring, when particle is in a ring, that is a problem like that in physics. So we are trying to solve that. Expectation of P comes out to be some finite, some value. So I don't think it is applicable to all the possible potentials, but to some certain cases that thing works, but not for all. That's what I guess.
Yeah, but it will also be very useful result which you can try if under what conditions it will be 0. Like that, if you can also derive, then that will be good.
I think it is for stationary bound states. I think that's a problem in some Shankar. Telling the truth that for all stationary bound states, the thing is 0. And I guess that's the question. If possible, I'll try to spot the questions.
Okay. Okay, so I think if there are no questions,
So one more thing.
Yeah.
So you said that previously the quantum system evolves using unitary operations. So the norms keeps getting preserved. So we know that measurement is a non-unitary discontinuous thing. So when that happens, all that we know about it is that from a wave function we get into a Dirac delta function.
If you do position measurement,
And for any other,
it will be the eigenstate of that operator.
so since a delta function works in a way like we are calculating the probability inside a whole volume integral, so delta function will take out that like usually inside an integral delta function takes out the value of a function at a particular point and picks that out.
Correct.
So can we say that the measurement that we are doing introduces a delta potential inside a delta function potential inside that particular wave function, which extracts the whole state?
No, it's not. It's not like that. See, Dirac delta function is an eigenfunction of the position operator in the coordinate basis. That is why we are getting the Dirac delta function when you measure position. What happens if you measure momentum? The wave function after the momentum will be some e power ikx, because that is the eigenfunction of the momentum operator. Now, if you measure some other operator, some other property, then its eigenfunction will be the eigenfunction after the measurement. Whatever eigenvalue you got as the result, the corresponding eigenfunction will be the state of the system after measurement.
Okay,
So,
system.
Dirac delta function comes only in the position measurement.
So whatever eigenvalue that we get in the measurement corresponding to that function we
will be the state.
Okay, sir.
Hello, sir.
Yeah.
Sir, I don't get the vector space lecture, no, sir.
No, I have shared all the directory, I mean that entire folder with everybody. So you please
Sir,
check all the
I
lectures
think
are in the folder.
I think there was no not present that lecture, sir. I checked it.
There are 10 lectures and all the 10 lectures are there. Did you get the folder?
Yes, sir.
In that folder, everything is there. Lecture
Okay,
1,
sir.
lecture 2. Is there any duplication?
No,
No, sir,
sir.
I
I
don't think
don't.
Yeah, I think it is there.
Okay, sir. Thank you. I will check it, and if there any issue, I will inform you, sir.
If you want, you just tell me the date, then it will be easy for me to check.
Actually, that day I was not present in the class. That's why,
So
sir.
then you will know the date, no, on which day you are not present.
Oh, okay, sir.
So just
Yeah.
tell me the date, then I will check.
Okay, thank you, sir.
Okay. You will-
Excuse me, sir.
Yeah.
Hello.
Yeah. Tell me. Hello.
I'm audible.
Yes. Go ahead.
Sir, this is suggestion like, hello.
You are heard. Tell me.
So this is not a question. Just I need some suggestion, like how to think. Like I just want to ask how to think more, like more mathematically oriented. Because when I try and study, I think more in the logical terms or like more theoretical terms. Somehow I am not able to go deep into mathematics. Obviously, as you do, that's my like inspiration. So how to how to improve this skill like mathematical, like how to develop my whole this thing more mathematically than logically or theoretically.
The issue is something like this. What you are saying is a general problem which I think all physics students face. Our physics students or teachers alike, they face this problem because the learning of mathematics in physics is different from learning pure maths. Okay, so that way I think this problem will be there with everybody. But then one can always try to ask this way of doing it is also important. That is, you formulate things logically and make some hand waving argument, give a heuristic reason. This is also important because sometimes a very rigorous thing will come only later. Initially, we get a feel, then you get some argument, you give some hand waving argument, or maybe you give some logical flow of thought. All this is also important. So if you are thinking along that direction, you don't have to feel bad about it. That is also fine. But then at the end of the day, if you feel very excited about doing some mathematics rigorously, then it is a good idea to learn it slowly. For example, one of the book which I can think of is that Real Analysis by Walter Rudin, where that is the probably first book which mathematics students study in BSc or MSc Maths, where the ideas of real analysis are discussed in such a way that you get to understand this theorem, proof, lemma, axiom, this kind of knowledge or language. And then slowly you can, whatever you want to ask your questions, you try to frame the questions in that language so that you can improve uh, just putting it in that language. Then the rigor will come slowly.
Okay, sir. The thing is, like, I am like, I can be satisfied with my logical thinking, but it's not very much convincing to others. Like when I express this to others, so they need like something more, like more detailed to it. So I like this logical ideas have a limit to me. Like till the point of only I can, construct that ideas, logical ideas, and thought. After that, I am limited. Like I can't go beyond that.
Yeah. I know that most of the times having some idea is better than having no idea. So it is always good to continue thinking like that. But then definitely, if there is interest and if there is time, then you should definitely learn to be more rigorous and then learn some basic pure maths language and then try to address your questions in more concrete fashion. Possible. As one book I would suggest is that read Real Analysis by Walter Rudin. Okay, so I think we can leave.